Okay, here we are in the last video for Unit 10. Hooray! So, we just left off talking about network solids. Now we're going to talk about molecular solids. And these are those solids where molecules occupy the lattice positions. What we mean by that is they're covalently bonded, but they're in a lattice structure. So these guys have strong covalent bonding, but weak forces between the molecules. So we're not talking about bonds between the molecules, but pretty weak forces between the molecules. As those intermolecular forces increase, of course the melting and boiling point increase. That's what the rest of this chapter has been about. If it's London dispersion forces, the strength will increase as the electron cloud increases. So what's that mean? A bigger molecule will have more London dispersion forces. Seems kind of obvious. Our dipole and hydrogen just depends on the polarity of the bond and how many hydrogens we have hanging around.
Water is a molecule made from non-metal elements. In the solid phase, these covalently bonded molecules are attracted by weaker dispersion forces. Long-range order exists between molecules that pack in regular formation. Molecular solids are relatively soft and have low melting points. Crystallized water occurs in many interesting forms, including snowflakes.
So when they showed us that picture there of the crystallized form, what that's saying is we just have some weak intermolecular forces that are making it look like a crystal. That's all a snowflake is anyway, is crystallized water. How about ionic solids? These are those super strong forces between oppositely charged ions, aka metals and nonmetals, and they have these high melting points, high boiling points. They're really stable. As our size of the ions gets smaller and our charge gets bigger, our lattice energy gets bigger. We talked about this in class. So we have to think about the amount of energy because their nuclei are closer to one another rather than farther apart. This makes it more stable, gives it a higher melting point.
Sodium chloride is typical of ionic solids. The crystal contains alternating sodium cations and chloride anions packed in a three-dimensional array. Ionic solids are brittle if deformed and will fracture along planes of packed ions.
So notice how when that guy fractured, it was right along the middle of that structure, straight in between two ions, essentially all the way down. That's how it'll always work for an ionic solid. It's not breaking the bond, it's just separating the crystal structure. So here's a good little table to show you how to remember these guys. Okay. How about phase changes? In any liquid, we have this kinetic energy. And we know that as temperature increases, average kinetic energy increases. But as our temperature increases, the ability of these molecules to collide increases. So look at this y-axis. Portion of collisions with the respective energy. Portion of collisions that have enough energy. Well, the more energy we put in, it's actually looking like the more collisions we'll have over time versus putting in a bunch of energy at the beginning and our collisions slowing down later. This all has to do with momentum and physics and the way energy is carried throughout time. Well, what would be better? It depends on the situation. If I want something that's going to keep a lot of energy for a long time, I need to put more energy in over time. If I want something to happen really quickly, I'm going to put in a lot of energy at the beginning and not need to get as much out at the end. Now, when something's evaporating, those particles that have the highest kinetic energy overcome those intermolecular forces within the liquid and evaporate to become a gas. And we know that evaporation is a liquid to a gas, but what's really happening is the particles at the surface are evaporating. We have to get that surface to evaporate before we can evaporate the rest of the system. Technically, evaporation is a cooling process because those particles with the highest kinetic energy move away and the rest of the kinetic energy of those particles decreases, which is crazy to think about. But think of a puddle evaporating. Only the top's evaporating. And when it evaporates, some of that kinetic energy isn't being lost, but is being transferred. It's going to another area. So every time there's a molecule that evaporates, the next one has to gain more kinetic energy by heating up. So if we have this open container, the particles will diffuse away. Heat will be absorbed by the surroundings, and the cycle continues until everything evaporates. If we're in a closed container, they're trapped. They build up, they collide with one another, and that's when we have condensation. It's because they lose that energy from colliding, and they recondense and turn back into liquid water. Equilibrium occurs when we hit this rate where evaporation and condensation are equal. And here's a good example. At first, they're all evaporating from the surface, but over time, all these collisions start occurring, and the same amount that are evaporating are also condensing. So, over time, the rate of evaporation is constant. But because look at here, over time my rate stays the same. But down here what's happening is my rate of condensation is increasing until we end up with equal rates. And that's when we've hit equilibrium. So how about vapor pressure? We've talked a lot about this. But what vapor pressure is it's saying at equilibrium how much water is there in the air. The systems at equilibrium, when no net change occurs, they are exactly balanced out. Liquids that have strong intermolecular forces have relatively low vapor pressure because there isn't that much water in the air around them, because it would rather stay as a liquid. It would rather hang out where all those intermolecular forces are keeping it happy. But if they have weak intermolecular forces, we consider them to be volatile. They evaporate easily. Think of when you open nail polish remover and everybody in the house smells it. That's what's happening here. They're turning into vapor, and the vapor is carrying throughout the room. So vapor pressure increases significantly with temperature because, of course, they want to evaporate when they get warmer or get more energy. So they're going to try to leave that substance and evaporate. Here's a good example of a couple different items that we're measuring the vapor pressure above. Over here we have this pressure at 760 torr pushing down, and inside the tube we have our level coming up. Look what's happening here. We have water vapor inside the tube instead of a vacuum. Well, that water is pushing down, I'm going to assume it's mercury in here, pushing down on the mercury and changing the water vapor on the outside. Well, what if instead I put ethyl alcohol in here? Well, it's going to push down with an even different amount of pressure and change the vapor pressure on the outside, on and on. Okay, it's going to change depending on what we have inside our tube here. It's going to affect the vapor pressure on the outside, just like when you open a can of soda and the pressure changes. So here's, very similar to our solubility charts, a comparison of vapor pressure and temperature. As temperature increases, the vapor pressure of water increases until it hits 100. What's happening there? Well, it's all turning into a gas then. Over here, ethanol, as temperature increases, it has an even lower boiling point, and then diethyl ether, super low, really low boiling point. We would have to apply hardly any energy to that. Now there's these two guys that came up with an equation, and I always think of Santa Claus, but Clausius-Clapeyron equation, and they're showing this relationship between vapor pressure and temperature. Looks kind of complicated, but essentially we're saying vapor pressure, P, we take the natural log of that, and we put it equal to our enthalpy of vaporization, or our change in energy, with a negative in front, over that R constant we've seen before in the temperature in Kelvin, and we add to it this constant that's associated with whatever liquid we're talking about. So it has this general form on the last page, but this is breaking it down even further. Look what it's similar to. Y equals mx plus b, which is very familiar algebra, and something that helps you draw graphs and figure out slopes. So essentially what we're saying is, if we plot this on a graph, the slope of the line will equal our vapor pressure divided by R. because that's the same as saying mx plus b. So it allows us to calculate these vapor pressure at different temperatures, and it also allows us to make graphs. This is actually part of the reason we have a phase diagram. So this looks really complex, but it's just comparing phase and temperature. Don't stress too much over it. But if we ever do have to use this equation, we have to make sure our units match, because we can't divide something that doesn't match. And of course our temperatures have to be in Kelvin. So let's think about boiling. As we increase the temperature of a liquid, vapor pressure increases until the liquid becomes equal to the surrounding atmospheric pressure. What happens? It boils. It evaporates. As we increase the pressure, boiling point increases. That makes sense. We can't overcome that pressure unless we put more energy in. Normal boiling point is talking about at standard pressure, so 1 atmosphere.
The changes that occur as energy is added to a solid can be summarized by a heating curve. This section of the graph represents water in the solid state, or ice. Starting at a low temperature, we see that the temperature rises as energy is added. In this region, the added energy increases the motions of the solid molecules, but the molecular motion remains centered on a fixed position. This section of the graph represents the melting of ice to form liquid water. When the curve abruptly changes slope to 0, the solid is melting. Here, all the added energy is used to overcome the intermolecular forces holding the water molecules together in the solid structure, allowing the water molecules to move around more in the liquid state. There is no further change in temperature until all the solid is converted to liquid. This section of the graph represents water in the liquid state. Further addition of energy causes the water molecules to move around faster, increasing their kinetic energy. The water molecules are attracted to one another by hydrogen bonds, but the rigid structure characteristic of ice is no longer present. Water is more dense than ice because the structure is more mobile and the cavities present in ice are no longer maintained. This section of the graph represents the vaporization of water. In this area, the temperature remains constant again, in spite of the addition of energy. The added energy is used to overcome the intermolecular forces between the molecules in the liquid, changing the molecules into the gaseous state. The temperature remains constant until all the liquid evaporates. This section of the graph represents water in the gaseous state, or steam. Addition of energy raises the temperature because the kinetic energy of the molecules is being increased, and the molecules are moving around more rapidly. The molecules in the gaseous state are far apart and relatively independent of one another.
So hopefully that was a good refresher there on your heating curve, and you should remember all that stuff as well as the 3 equations that go along with it. Now what about a phase diagram? Remember what these guys look like? Solid, liquid, gas in our 3 different phases here. Solid on the left, liquid in the middle, gas on the right. We're comparing temperature and pressure with this guy. Our triple point means all 3 exist together. Now, that's what I just explained, triple point. I'm running out of time on my video, that's why I'm rushing here. They're all in equilibrium. What about our critical temperature? That's the tip of our graph there, where we can't go any further because we would end up liquefying anything it comes into contact with. Critical pressure, same thing, the tip of our point where we can't go any further. We call both of those critical points. Now density, this talks about the way the line is sloped, but I have a better way to show you. Look at this little dot right here. If I go straight up from it, it's going to tell me, if I go straight up from my triple point, which phase is the most dense. So what's the most dense here? Liquid. Now what if instead my line were coming over like this, and when I went straight up I was in solid? That would mean my solid was more dense. Quick way to remember that. So that's chapter 10. Thanks for listening. Hope you're enjoying your spring break. Hope you got everything filled in. If you have any questions, you know you can email me, and I will see you very soon. Bye.